as our remark 4, okay, we define two planes to be parallel to mean that their normals, rather their normal vectors, are parallel. And perpendicular if, again, their normal vectors are perpendicular. Okay. This, of course, is, according to the geometry, quite meaningful, and so this will be our comments. Okay. Let us see some examples of planes. Certainly, we will be using geometry quite a lot, our common sense in 3D space as well. Well, as a first example, okay, let us consider the xy plane in space. Since the vector k is perpendicular to the xy plane, and the point, well, any point in the xy plane, why not the origin, okay, is on the xy plane, its equation is P0P dot K is 0. Now, what this means, of course, is that this being P minus P0, which, of course, is xyz minus 0, 0, 0, and K being 0, 0, 1. This means that Z is 0. Okay. So this is the equation of the xy plane. Similarly, x is 0, respectively, y is 0, are equations of the yz, respectively, xz planes. These are vertical planes on top of the x-axis and below, of course, and the y-axis, respectively. Now, let us be a little bit more specific. Okay. Let us find the equation of the plane determined by the 3 points. The first one would be 0, 1, 0. The second one, 2, 1, 1. And the third one, 1, 0, 1. Okay, we may have a little doubt that if they lie on a single line, we would have infinitely many planes determined by these 3 points. Okay, because clearly, if you have, okay, say, a line, and if you have 3 points on it, any plane which rotates around this line okay, would be determined by these 3 points. But here it's not true, as we will see at the end. Okay. Let us look at the picture a little bit. We have a plane to be determined, and we have 3 points on it. Okay. Now, to write down the equation of a plane, we need 2 data. One is a point. We have many. It's okay. We can take any of them, and a perpendicular vector. Okay. Now, a perpendicular vector, an n here, this is the problem here. So to find n, okay, we can look at these 3 points. For example, okay, we can look at these vectors. Both of these vectors would be on the plane, because the endpoints are on the plane. At any rate, they will be parallel to the plane. So, okay, we want a vector which is perpendicular to both of these vectors. So, if n is perpendicular to the plane, then of course n is perpendicular to P1, P2, and n would be perpendicular to P1, P3. Well, since we want to find n, a vector perpendicular to 2 given vectors could be taken as their cross product, because the direction is not important. So we can take n to be, say, P1, P3 cross P1, P2. Okay. Now, when we look at P1, P3, we see that it's P3 minus P1. Okay, so that would be, okay, in here, P3 minus P1. So it is 1 minus 1 and 1. Similarly, P1, P2 is P2 minus P1. So it would be 2 minus 0, 0, and 1. So 2, 0, 1. Thus, n can be taken as the determinant of I, j, k. We are taking the cross product. So I put here P1, P3 first. So it is 1 minus 1, 1, and 2, 0, 1. And recall how we calculated determinants. We have our ijk's here, and 1 minus 1, 1. Okay. Well, I will not calculate it, the long way, as in here. Okay. But the cofactor expansion is easier, so I'll just write down the result. Okay. That would be minus 1, and that would be plus 1, and finally 2. Let me see. Yes. Okay. Now we know a point, and we have a perpendicular vector. So the wanted equation, okay, P0, P dot minus 1, 1, 2 is 0. Now, of course, this is x, y, z minus any point on the plane, for example, P1, so say 0, 1, 0. Or P2, or P3. Any of them could be used here. Now, let us simplify this a little bit. It says actually that we have x, okay, y minus 1, and z dot minus 1, 1, 2 is 0, or equivalently, that's minus x and plus y minus 1 plus 2z is 0. Okay. So this is the equation of the plane passing through these 3 points. Now, a remark maybe, okay. Note that P1, P2, P3, okay, are not collinear. Okay, if it were true, if they were, okay, P1, P3 cross P1, we calculated, right, these things. This would be the 0 vector. Okay, because if they were on the same line, these vectors P1, P3 and P1, P2 would be parallel. So cross product of 2 parallel vectors would be the 0 vector. But it's not the 0 vector, and so they were not on the same line. Okay. Well, as a third example, okay, let us find the equation of the plane, okay, which is parallel to the plane whose equation is z is 2 minus x minus y, and passing through P0, which is 0, 1, 2. Okay. Note that here a point is already given, so we only need to find a perpendicular vector. Now, because the 2 planes are parallel to each other, their perpendicular vectors could be taken the same or a multiple of each other. So, parallel means, of course, the perpendicular vectors are parallel, so we can take n as, okay, the given, or actually it won't be correct, and as any perpendicular vector to the given plane. Okay. Note that okay, in the given plane, that's to say for z is 2 minus x minus y, okay, the given perpendicular vector is not the coefficients of the x, y, z's. Okay. A perpendicular vector is not, okay, coefficients of x, y, z. Okay. The reason is it's not in the standard form. What does standard form mean here? It means that if it's given in the form, okay, P0, P dot, the vector is 0. Well, it is given that way, but the places are shuffled a little bit, so we put them in order. In other words, put everything on one side. Then it becomes, okay, x plus y plus z. The constant is not important. Okay. Now, we know that the coefficients, okay, so a perpendicular vector is 1, 1, 1. Okay. So we can take the same one for our plane. So the wanted equation would be P0, P dot 1, 1, 1 is 0. But this, of course, means that because P0 is 0, 1, 2, this is x minus 0, okay, y minus 1, and z minus 2. This is P0, P. Dot 1, 1, 1 means you multiply them by ones. Okay. Which, of course, happens to be x plus y plus z, okay? And the constant, we have here minus 1, we have here minus 2, so that would be equal to 3. So you see that the constant here, which was 2, became 3. It controls from which point the plane passes. Otherwise, the normal vector is the same as the original one. Okay. Well, as a fourth example, let us see the following. Actually, this is not an example, but it's an explanation. Okay. The plane equation in R3, okay, is a generalized form of a line equation in plane. That means we can define line equation in plane the same way as we did of a line in plane, right? As we did a plane equation in space. So, okay, let us see why this is true. Okay, say a slope, say a line has slope m and passes through P0, which is 0 some n. Okay, n is not an integer here, just a scalar, a real number, okay, in plane. In the usual Cartesian plane, we have a straight line, and the line is given by a slope and a point. Okay. Now, let us find a perpendicular vector to it. Okay. So, okay, we have some line. Okay. It passes through this point, and it has a slope m. Clearly, slope means if you take 1 here and m here, okay, so the vector 1m is parallel to this l because its slope is m. Well, we don't want a parallel vector, we want a perpendicular vector. Now, if this is parallel, then of course minus m1 is perpendicular to l because of the dot product. The dot product would be 0 by dot product. Check. Okay. So now we have a perpendicular vector to this L with slope m, and we know a point. So equation of L, okay, would be P0P dot minus M1. This is our claim. Let us see. What does this say after all? This is xy, we are in plane, minus x0, y0, but it is 0, n. So it is x, okay, and y minus n. Okay, the dot product says that you have minus xm plus y minus n is 0, or y is mx plus n. That means if we have a perpendicular vector and a point, then this plane formulation gives us a line in plane, in the Cartesian plane, in 2 dimensions. So it's a generalization of a line to 3 dimensions. Okay. Now the next question is, well, if planes are generalizations of lines from the plane, what's a line in space? Well, geometrically, of course, we have lines in space, lots of them, okay? So let us investigate this a little bit. Okay. Now, of course, we recall that a slope, that is a number, m, which is the slope, and a point, say P0, determine a line in plane, okay, in the Cartesian plane as we know it. Well, is the same true in the case of 3 dimensions? It is certainly not. This is not true anymore in space. Okay, the main reason is, of course, the following. We don't have a slope concept. Okay. Namely, since slope is meaningless in R3, for a line, of course. Why is this true? Well, how do you want to define a slope? Okay, let us see imitating what we had in 2 space. Okay. Suppose we have some line, okay, passing through, say, some P0, okay, and say this is our line. This is L. Now, it passes through a point P0. Let me use some color. Okay. It passes through P0, okay, and suppose it has a slope m. What is the slope? Okay. Well, we can define it this way. We can draw a perpendicular here, okay, and call this B and call this A. So slope is, okay, B over A. Could we define it this way? Okay, clearly not, because, okay, suppose we have a straight line this way where this ratio is fixed. Then, okay, start rotating the line okay, around this point, this straight line. That is, okay, consider rotations this way. Now, because this point is fixed, all the lines L prime, okay, when you rotate it, will pass through P0. And the ratio will be the same, because this is the same right triangle. And so it follows that, okay, any L prime obtained by rotating L about, okay, a vertical line through P0 have the same end. So, conclusion, slope and a point do not define a single line. Okay. By the way, the slope concept is meaningless in R3 because you can go backwards, rightwards, down, or up and look at the line from different angles. And you may define lots of slopes that way. So this approach not being appropriate, okay, we need, okay, to look at a line in plane, okay, in a different way. Okay, what could be this different way? Well, vectors are quite useful in such cases. Say we use vectors. Okay. Now, what does this mean? We are in plane now. Okay. And say we have, okay, a line L, and we have a point on it, and we have a slope. Well, every line is characterized by a point and its slope in plane. Well, looking at the previous argument we had, that is, when we regarded the plane equation as a generalization of the line equation, actually we used vectors. So, I can obtain P on the line as follows. I can start from the origin, go to P0 as a vector, and then continue by a different vector to P. This is clearly true, namely, P as a vector, which would be something like this, okay? P would be P0 plus P0P, because this is P minus P0. So this is trivially true. Now, I don't want to use slope as a number, but I can use it, as we observed a few minutes ago, as a vector parallel to L. So, suppose V is any vector parallel to L. Then, okay, we see that P0P can be written as a multiple of this V. Okay. Well, why? Because if V is parallel to L, P0, P is another parallel vector to L, so they are parallel to each other, so one is a multiple of the other. Well, this tells us that P equal to P0 plus TV describes the point P on the line. This is true for every P. If I change P, okay, on L, the same equation will be true, but T will change. So if in this picture, for example, okay, if this is my V vector, which is parallel to L, okay, if it directs this way, it need not to, then for this P, T will be positive. But if P is on the other side of P0, T will be certainly negative. But T is a real number. Well, this tells us that we can characterize points on L exactly this way. Now, conversely, suppose we have two such vectors. That is, we take P0 vector, and then we take a multiple of V here. Okay? Then we find a point on L. So both ways it works, which means it's the line equation. Okay. Okay, so thus, okay, any point on L is given by P is P0 plus TV, okay, and conversely, okay, P0 plus TV is always on L. Okay. This characterizes L. The equation P is P0 plus TV characterizes L. So this is the line equation in space. Now, the picture was drawn in plane. But clearly, when we consider vectors with three components in space, the same geometric structure prevails. Thus, okay, since geometry of vectors is exactly the same in R3 as well, okay, or Rn, which we will not consider now, okay, as well. This is the line equation in R3 also. So we have this formulation of a line in space, we need two data, a point and a parallel vector. Okay. So let us investigate this a little further. Okay. Well, before we go into a little bit detail here, let us see the following. Right. Let us see the role the vectors play here. Maybe a good will about vectors would say the following. A good thing about vectors is that they do not concern themselves about the dimension. That is, whether it is in R2, in R3, or maybe in higher dimensions, all of these would work. So you could define a line in R5 space exactly the same way, for instance. Okay. Now, a little bit more about this equation. What does it really tell? Well, let us consider the forms of line equation. First of all, we have this. As we see, there are vectors in it. Everything is a vector except t. This is called the vector form. But even though it's a single equation, it looks like a single equation, it's not. Okay. Now, this is a vector equation. So, it is actually three scalar equations. Let us write it down. Okay. It says the following. Okay. X, Y, Z, of course, we're in space, is x0, y0, z0, plus, okay, t times A, t times B, t times C, where V is ABC. So given components, actually it says this equation. But so, it says that x is x0 plus TA, y is y0 plus tb, z is z0 plus tc. Note that t is a parameter here, and we have three scalar equations now. This is called the parametric form. It means exactly the same thing as before, but instead of vectors, we use three equations, depending on a t all the time. Okay. Now, or we can start from here, and in parametric form, okay, let us eliminate t. What does that mean? Well, t is, let us write it from the first equation, it is x minus x0 divided by a. Okay. But at the same time, from the same equation, t is y minus y0 over b. And from the third equation, it is z minus z0 over c. This is called the symmetric form. Okay, each form is equivalent to the others, of course, but okay, they have their own advantages depending on the question. Okay. One, of course, problem could occur if A, B, or C is 0, which certainly can happen. What about that? Well, in some notations, one uses 0 here, which some mathematicians don't like. Better is the following. If, for example, A is 0, we write, okay, clearly if A is 0, it means x is equal to x0. So we write x is x0, and we have the same equation, valid still, y minus y0 over b is z minus z0 over c, and so on. Okay. Clearly, if A, B, C are all 0, you don't have a line, you have a single point. So it is meaningless. Okay. So if one of them is 0, we write the equation like this, and the others are written that way. Okay. This is the symmetric formulation. Now this tells us two things. Actually one thing. Let me call it a remark. Note that the line equation looks like one equation in vector form. It's not. Here it looks like three equations. It's not, because t is free. And from the symmetric equation, we see that there are two equations, two scalar equations. So, okay, observe that a line equation is actually two scalar equations, each of which, now looking at these equations, we see that we just have just x, y, or z. No squares, okay, no exponential signs, etc. So, okay, each of them is a plane equation. So, this says that a line equation is actually two plane equations. Well, this is not surprising. Since a line is intersection of two planes. So a line equation means these are points which satisfy the equations of both planes. So it's the intersection of two planes. So this is something we certainly expect. Okay. Well, let us have some examples. We will have many of them. Okay. The question is, find the equation of, well, it will change from problem to problem. So let us say of the line, okay, passing through a point, say 1, 1, 1, and perpendicular to the plane pi, which is given by x plus y minus 3z is 3. Okay, the geometry is clear. We have a plane, pi, okay, and we have a point, P0. Clearly, P0 is not on the plane. You can put 1, 1, 1, see that it's not satisfied. So we have a point outside, okay. We want to drop a perpendicular to pi. So we want the following. Line. So this is the question. Well, from the geometry, we immediately see the following. Since the normal of pi is parallel to L, okay, we can take it as V. We can take V. Usually we show it with VL, okay, to be the same. Because of perpendicularity, and normal here is certainly parallel to L, and that's all we want. So we are finished. So the equation is P is P0, that is 1, 1, 1, plus T times normal. Now what's the normal? Well, everything is on one side, it's in standard form, so it's just 1, 1 minus 3. So this is the equation wanted. Okay. Let us find, this is not an equation problem, but nevertheless, find the intersection point of the line L given by x minus 1 is y minus 2 over 2, which is z over 2, and the plane pi, which is x plus y plus z is 1. Okay. Now, looking at it from afar, we see that actually, okay, we want to find the intersection point, which means we have to find three things, three coordinates of this point. Well, we have three equations for it. So we have three equations, namely 2 from L, 1 from pi. Okay? To solve, okay, the intersection point, x0, y0, z0. So we can use direct substitution. Okay. Or, okay, which is sometimes simplifying, we can make use of the parametric form. Namely, we can directly do that, or, okay, we can use the parametric form. What does this mean? This means that write everything, x, y, z, in terms of t, and put them in here, solve t. So, write x, y, z in terms of t, and then put it, or rather put them, in the plane equation. Let us do it. Well, the symmetric form is given. So, we need to parameterize it. The standard way was, say t is equal to each of them. So, put t equal to x minus 1, which is y minus 2 over 2, which is z over 2. So, x is t plus 1, y is 2t plus 2. Well, let me see if I got everything correct here. Right. And z, of course, happens to be 2t. And then put them in equation of pi. That means you add x plus y plus z. So it is t plus 1 plus 2t plus 2 plus 2t, and that's equal to 1. Which says, of course, that you have 4, 5t, and you have 1, 3, and minus 2. So, t is minus 2 over 5. Thus, x0 happens to be t plus 1. y0 happens to be 2t. 2 times minus 2 over 5 plus 2. And, of course, z0 happens to be 2 times minus 2 over 5. So this is the intersection point wanted.